great pleasure to introduce our next speaker, Mario Serna, on going to be talking on visualizing Kaluza, Klein, and other hidden geometries in side gauge theories. Great.
Okay, I think I'm sharing the screen. Does it seem to be working?
Yep.
All right. First, I wanted to thank the organizers very much for both organizing the interesting set of topics and for giving me, a relative amateur in this process, a chance to talk. I'm obviously in the Air Force, so this ends up being my night and weekends projects, which I thoroughly enjoy. And as such, please interrupt and ask questions as things may come up. I'm trying to keep with the spirit of having this thing at a very high level. So I apologize for some parts that are pretty introductory, and looking forward to the interactions. Thank you. So the goal of this talk is to show stuff that I think people have been mentioning for a long time when they teach these aspects of physics, and to make it a little more concrete. So the first part I wanted to explain was something about why it's valuable to have different ways of representing the same physics, and show some examples in the past where that has demonstrated new physics discoveries, and then show 3 different approaches for understanding the geometry that's underneath of electromagnetism. And last, see what comparing these things implies for possible new things. So let's see. I'm no longer advancing. Let's see why I'm not. There we are. So kind of here's a pictorial map of the process of the discussion. So at the bottom, is the mouse visible when I click, or is it?
Yes.
Okay, so at the bottom of the process is kind of the standard electromagnetism introduction, where electric and magnetic fields are derived from vector potential. And for a long time, this concept of this alternate representation was considered a nuance, allowed you to represent things through just another way, through the vector potential. So the vector potential then leads you to a way of expressing E and B. Was this vector potential real? We don't know. That leads to this thing this Aronoff-Bohm effect that was eventually is a reasonable argument to say that the vector potential may be more quote unquote real than the electric and magnetic fields. And from that, I then step backward and say there's 3 different ways to get to the vector potential that have been published by other people. And the talk is really about interconnecting these different ways and showing pictures that we kind of that make very concrete things that we hand wave often. So, you know, showing physics from the same material from different representations has been in tradition through physics for a long time. Hamilton Lagrangians versus Newton's laws, gravitational fields versus the Newton's force law, path integral integration versus canonical quantization, and of course the example I'll kind of go in a little more detail here, the vector potential. So the vector potential, you know, as we all know, and again, I'm thinking this is a very broad mathematical audience, that the vector potential is pretty common, but it comes from this symmetry that you can add the derivative of a gauge of some arbitrary field, and the physics remains invariant. So you've got some symmetry that's introduced. That symmetry gives you a new tool. That new tool is not clear if it leads to something new in terms of a real understanding. So what we do is we go to the example of the solenoid, where you put a magnetic field inside of a closed region that doesn't exist outside. And outside here, the magnetic field is all 0. And the quantum interference gives you a chance to be able to test this. So you can look at what the phase shift is from computing the paths along both different ways around a solenoid. And you find that there's a phase shift introduced by the integral of a loop around the solenoid from the vector potential, which if you integrate non-locally through the body of it gives you an expression for the magnetic field. Because there's a sense that a lot of physics, the expression that uses the magnetic field is non-local, which gives you a preference for why you think that the A may be the parts that are in contact with where we think the electron is traveling probably have a little more sense of being real in a way of trying to dig down to the underlying causes. And sure enough, physics shows that when you put this a solenoid in there with a magnetic field and you make the electrons travel around, you can see the interference fringes shift as the strength of that magnetic field changes, which shows this is a 1960s experimental demonstration that vector potential seems to have a deeper reality than the electric and magnetic field. So all that is to say that there is a value to this structure. And now we're going to go to the kind of the way of connecting this to the theme of the mathematics, the differential geometry. So basic differential geometry says if you parallel transport a vector around a loop, the angle change after going around that loop gives you is some way of measuring that curvature that you've gone through. So what we'll do now is we'll do the same thing, but now for electromagnetism. By the way, I can't tell if there's any comments in the text things. I didn't realize that blocked my view of that. So if there,
I don't think for any comments yet. No.
Okay. So this is thus far a start where I'm still trying to do very introductory pieces and background, but that same concept for measuring curvature, if you do it with electromagnetism, measuring the angle change around a loop, you a couple of steps away, if you do this over an infinitesimal square, leads you to an expression of the magnetic field as the measure of that angle change around a closed loop. So in differential geometry, we've got this comparison between differential geometry, the way that we traditionally teach it, and the vector, the gauge theory, the way that we traditionally teach it. And you have all these analogies. There's the covariant derivative, the connection, the curvature tensor being the commutator of two covariant derivatives, the angle change from integrating around a closed loop of some sort of a vector. In the case of Riemannian geometry, it's a vector. In the case of gauge theories or electromagnetism, it's the wave function. You have a very clean pictorial representation in Riemannian geometry of how to think about what this geometry is. And the goal here is to show three different ways of seeing what might be the associated representation or picture on the gauge theory side. So Kaluza Klein models are obviously very big in string theory and were developed long before string theory. And they imply the presence of a fifth dimension that somehow gets curled up and manifests as the electromagnetism. Grassmannian manifolds it came from a theorem that from Narashima and Ramanan, who were trying to do something like Nash did. Nash showed there was an embedding representation for every Riemannian manifold, and inside of a Euclidean space. So you put a Euclidean space, you put some sort of an embedding in there, and you can derive any metric that was able to be generated. And they did a similar representation for vector potentials. And last is a hidden spatial geometry from where you're able to map a Riemannian manifold to a Yang-Mills theory into a Riemannian manifold. And that was done by Ken Johnson and Dan Freeman at MIT in the 1990s. So I'll go into a little more depth for each of these pictorially and show a little bit about them. So mathematically, the Kaluza-Klein comes out as a metric. The Grassmannian manifolds comes out as rectangular, not square tetrads, where you're looking at kind of a way of embedding a tetrad into a larger dimensional space and then having your vector potential come out from this, from the induced connection on that, on this family of tetrads across space. So you're able to get to any SUN gauge representation from this kind of a mapping. And the hidden spatial geometry used tetrads that were basically 3 by 3 in the case of the case that Ken Johnson used. In our case, 2 by 2 for E&M. But they use these tetrads to come up with a Riemannian metric, and using the standard tetrad covariant derivative that you might come up with to see where it fits in the mathematics. All right. So let's see. So to show these things pictorially, what we'll do is we'll start with the Grassmannian approach, and we're going to show a 2-dimensional plane inserted into a 3-dimensional embedding, and that there is this 3-dimensional embedding is common to each point in space and time. So imagine this is the y dimension and this is the x dimension, and inside of each point there's a 3 space that we can compare with, and there's a 2 plane identified within that 3 space, and that 2 plane is different at different points in space. So Narasimhan and Ramanan showed that by looking at these 2 planes as they change around at different locations, you can induce a vector potential, and that vector potential therefore you can represent that vector potential by a series of planes at different points in space-time embedded in some higher dimensional space. For a general case, it has to be more than 3. So what I'm doing here in order to visualize it is coming up with special cases that can be done within 3 spatial embedding dimensions, which is not all cases, but enough cases so that you can at least see some examples. I'd like to pause here because this is typically where everything builds on this step, and this is the step where it's often not clear. So I was going to open it up for questions for clarity, or just pause for a moment. So if there's no...
Actually, may I just ask a clarifying question?
Sure.
So you referenced SEER here. Is this basically saying you're getting your connection, as in the ADHM construction, by projection of the flat connection or trivial bundle?
I think that's correct. I've looked up ADHM about 5 years ago, and I think that was what I understood. Fantastic. ADHM, I think, had some extra symmetries that were not needed.
Yeah.
So this is a simpler version of ADHM.
Right. Thank you.
No, thank you. That's any other? Sorry, I'm having trouble controlling my page on this. So to show how electric and magnetic fields manifest in that construction, you take a vector on your 2 plane, you parallel transport it around a closed path. There's a small angle change. And if the loop you transported around was purely spatial, it ends up being a magnetic field. If this way is purely spatial, it ends up being a magnetic field. If the loop you transport around has a space and a time dimension, then you end up with an electric field. So this is the Grassmannian representation that, like you said, relates to the ADHM representation as well. And another way of seeing, so now we're getting to the case where we're going to show a very clear, a rigorously worked out example where I draw a pattern in space so that you can see that this represents, the inner line represents the direction in time, the outer line represents the direction in a spatial direction. And that, when you're mapping that over here to this side, you see that this is the way the spatial positions correspond on this set of planes. And this particular way in which these planes shift comes out as being a y-polarized plane wave. So this axis is the y direction, and this axis is the x minus ct direction where you see time propagating. And you know, the pattern obviously looks like something you might recognize. You can kind of try and imagine what pattern has a flat plane on the top and kind of planes that rotate around on the edge. And there's some stuff that's hinted at geometrically here, but you can't quite see it. The part that's exciting is that this actually is a very clear way of seeing a gauge invariant y-polarized plane wave. A gauge transformation basically just changes the axes, these two red vectors that define the plane. It rotates them so they define the plane again, but just rotates them on that same plane. So gauge transformations are very easy to see what we're doing with, and the underlying geometry, the planes, is gauge invariant. So now we get to the case where we map this onto the structure that Ken Johnson had developed at MIT with Dan Friedman. They said that there was an underlying spatial geometry that came out with a metric. And what they ended up doing is showing that if you take this surface, which I'm embedding in 3 space again for simplicity, and project these spatial positions onto that surface, when you try and calculate out your connections, you'll end up with the vector potentials that are associated with some type of curvature, in this case, the y-polarized plane wave that we had in the previous slide. To connect that back to the Grassmannian model, the tangents at each of these positions ends up being, the tangent planes at each of these positions are what you would see from the Grassmannian approach. If you connect them into this overarching shape, you get the Ken Johnson approach, the hidden spatial geometry approach. And the third approach is Kaluza Klein. And when you see things like Brian Greene talking about fabric of the cosmos, he depicts the Kaluza Klein as showing a little loop at each point in space-time. And those little loops end up being a loop on that tangent plane that Grassmannian had, that the Grassmannians showed. So describing the picture between what Brian Greene might represent, this is a mathematically rigorous y-polarized plane wave in what we would see as a y-polarized plane wave using Kaluza Klein. So this is what Kaluza Klein would give you, and each of these little loops is in principle, the compactified dimension that you would have in string theory. So let me pause again for questions or clarifying thoughts. So, oh, good. So, all right. So I'll get to the last piece that I think starts to have, where I'm hoping to generate some discussion. In 3 different representations, when we get to the gauge invariant way of representing in this case, electromagnetism, there is a time dependence to the electric field. So the electric field that we might consider constant has an underlying geometry that is changing in time. That, if we work it out for a constant electric field, the time dimension, this is a representation of a constant electric field. You have a time dimension and you see that the underlying geometry is clearly changing. that underlying geometry is represented from the hidden spatial geometry part, ends up looking kind of like the cone, the body of a funnel, or the inside of a funnel, and the time dimension loops around that funnel in some periodic manner. I've got a video I can show of that, but what's surprising here is that you have a time dependence to things that we consider static. And the question should come, or at least comes to me, what does the source of that time dependence? So if we look at a electric field as being caused by some source, there's a periodic dependence of the electric field that results from that source. Is there some time dependence on that source that's causing that? And should they be connected? So the second part that's I look at as kind of an unanswered question is, we see linear superposition working extremely well in normal physics, but linear superposition works nicely at a vector potential level. But when you look at it at a geometry point, the geometries that you might be adding have very little in common, and it's not clear why geometry 1 plus geometry 2 equals geometry 3 in any kind of meaningful way when you look at it from the underlying geometry advantage versus the way that which we typically do on the lower way. So these are kind of two conflicting puzzles that I'm throwing out for discussion. With that, I think that concludes the main points of the talk, that there's 3 different ways of getting to your vector potential that I showed how they connect to each other visually. And they all imply some sort of a new time dependence that is more clearly gauge invariant. And that may be a place where there's some underlying tool that we can use to connect things that we thought were not connected in the traditional way of representing the physics. That I've open for questions, and happy to point to the Foundations of Physics paper that kind of goes into this in more detail.
I have a question about the Berry phase, because that's another way of generating the vector potential, correct?
Correct.
But you start with the Hilbert space, right? And then essentially you look at adiabatic transformations, right? You generate some adiabatic evolution on the Hilbert space, and you essentially take an overlap, right, between the states and neighboring states, and that's your connection.
Correct.
So how does that fit in this particular discussion?
So if I'm, and again, this is to me, the Berry's phase is that the generating of these, let me phrase it differently. This is a classical field theory representation of what you would think of as a singly quantized particle, a wave function, right? So whatever you do with the Berry's phase from the wave function point of view comes from having the underlying geometry or the magnetic field change to introduce that Berry's phase connection by having the background field pick up this type of structure for the vector potential. So the Berry's phase comes along from that same geometry that's imposed from the magnetic field. Did that make any sense, or am I missing the question?
Well, I was just asking how does it fit into any of these, but I guess you're trying to tell me that it does fit into this Grassmannian model. Is that what you're saying?
I'm saying that in the
because
Berry's
it is true that the projective space is a complex. So the projective Hilbert space obviously is a complex projective space, right? So
Yes.
And the complex projective space obviously is a Grassmannian. So Berry phase is really that, whatever, if it's CPN, whatever, UN over UN minus 1 cross U1, that UN minus 1, right, is really the Berry phase. I think that's what you're telling me, that it fits into the Grassmannian model. I guess I would agree. Yeah.
Okay. I'm more on the purely mapping the Berry's phase from the U1 side rather than the other structure that was there.
Well, I mean, U1 is just the U1 of the that defines the complex plane. In other words, the
Right.
U1 if you want the phase of the wave function. But
Right.
but in general, the Berry phase can be non-abelian, right? So
Right, and that's and this all generalizes to non-abelian. I just have not
Yeah.
done that work myself.
Okay.
So each of these structures.
Yeah, but
you
okay,
have to-
I agree. This is definitely fits into the Grassmannian. If you think about CPN as a projective Hilbert space for quantum mechanics, I agree. Yeah, that does fit. Okay, thanks. That's good.
Right. So what I'm curious on from anyone out there is, how do you connect? Or is there anything meaningful about having the electric field be time dependent? Because none of our other representations show an electric field being time dependent. We have the theory that we can always gauge transform it away from the time dependence.
I would say that's just simple relativity, right? So, I mean, depends how you want to think about this, but right, the electric field is not different than the magnetic field after boost.
Right.
But you're saying that you want to understand that just purely geometrically. I mean, in the Kaluza Klein, obviously you have some signature, right? You have a minus plus 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 or something
Right.
like that. So obviously you have relativity. If you're asking about the other Parnassians, I mean, like for example, in this Grassmannian model with Berry phase is essentially a unitary transport, right? It's a unitary evolution, right, which is generated by energy by Hamiltonian. So that's your time. So you can use that again to go from, if you want, electric to magnetic response. So as long as you have that, as long as you can boost, electric field is not different than magnetic, right?
That's the simple way of saying that. But what I feel happens is, if we look at flowing water, if you have a very smooth hose, it may look time independent because the water's flowing at a constant rate. It makes a constant arc out of that hose. Everything looks like it's independent of time, other than the fact that you've got a vector to represent, if you were to represent the flow with the vector. But there's something underlying in that hose. The water is actually moving, even though everything appears static.
Well, I know, but that's depend on the frame. You know, you can have a Euler description of that flow, or you can have Lagrange description of the flow. So if you want the manifest description, you know, where the velocity is a field, it's a vector, right? It's a non-relativistic field, if you want, that depends on time. Then you just go to the Euler description, and yeah, you have an explicit time dependence.
So because you have that back and forth, just like you said, you can choose which representation to get some set of answers, but one approach tells you there's something moving underneath, and that you haven't identified what that moving thing is.
Well, you have to tell me what do you mean by underneath, right? I mean, you know, you have to give me a reference frame.
Yeah.
So once you define the reference frame, then we can talk. And then, you know, within that, we can give a co-moving description, or we can give the one that is not. So, right, I mean, we have that choice. Of course, you know, the invariant quantities then do not depend on the choice.
Right. So the invariant quantities don't depend on the choice. You can choose those ones, but in only one of the descriptions do you realize that you have something else you can tinker with to address.
Well, yeah, co-moving description. If you want really to think about it, yeah, I would take that one. But yeah. I mean, relativity essentially telling you that, right? It doesn't really matter, right? As long as you have a description in which you can boost, right? The world is invariant under Lorentz transformations, then I can go from a magnetic field and generate electric field. I mean, they do that in the lab, right?
Right.
That's how they generate.
That's correct.
Right.
All that is the normal way of saying that you have different representations. What I'm trying to hint at is that there's water molecules present moving in the hose. We don't have a way of realizing there's water molecules present in that hose unless we dig down one layer deeper than either of the two descriptions to say that there is something physical moving.
Again, it's a really moot point, right? From the general theory relativity point of view, you can say that there is no time, right? Because of the Hamiltonian constraint. However, right, I mean, this is this, you know, discussion that I think even goes into interpretation. Do you have sort of a eternal block of space-time? In other words, as a mathematician, you just basically give this geometry and that it's eternal, or is essentially all generated by evolution of spatial things. You know, they called it presentism and eternalism. I think philosophers of science call that way. I think it's neither. In quantum mechanics, it tells you that you have a unitary evolution. So yeah, classically, you can choose these frames. You can have this eternal, and you can have this present, you know, presentism, whatever discussion. But I think the world is quantum, and in the quantum, you actually generate through the time. But I think that's more like a discussion of interpretation. Yeah.
So it's a discussion interpretation up until you ask where things come from. So in the hose, I push the water forward. In this case, we have a disconnection in our description between the electric fields and what causes them, right? We see
charges cause electric field. You say
so,
charges cause electric field. You know, I mean, it's an old discussion that goes back to Maxwell, right?
Right.
You see, Maxwell equation, you can introduce a magnetic field. If I just start from a static situation, just take Coulomb law,
right,
and Galilean relativity.
So
okay?
so charges cause it, and I love that that part you're saying.
Yeah.
So if charges cause it, you see a time dependence in the charge, because every particle has an e to the imt kind of wave function deep underneath of it, depending upon how you do renormalization and other goofy things.
Yeah, if you start with sources, then fields are definitely caused by sources. If you're asking how do you put sources and fields together, that's a different question.
And that's what I'm asking, is that last part, is the source, how does the field caused by that source? And when you step to this level where you're looking at the time dependence explicitly in a gauge invariant manner, the way that we describe them makes them be essentially disconnected. You're kind of manually putting in a source and manually getting out a field.
Yeah.
And the two time dependencies are not connected to each other.
And that ultimately goes to the difference between the excitations that cause the sources and the fields. The fields are always bosonic. All these quantities here that you're talking about from quantum mechanics, from the spin statistic point of view, they're bosonic. All the matter degrees of freedom, all the sources are fermionic. If you wanted to put these together, you would have to have some unified description. Let's say in supersymmetry, we don't have that in the real world, but at least mathematically, the sources and the fields are on the same footing, because you know fermions and bosons are put together. So if you have a supersymmetric situation, a supersymmetric model, if you take your electromagnetism and supersymmetrize it, you could do that, and even you can include gravity and so forth. Now, but we're not talking about the real world in that sense of water flowing. We're talking about mathematical, but precise. You know.
But no, that's actually your comment about the bosons and fermions is very deep on that. That is where I've been trying to figure out how to see that connection get more manifest because of that specific phenomena you just pointed out. And my hope is that by looking at this, you might be able to see a new way in which these things are tied to each other with a new constraint that may have some other manifest, something like the Avram-Bohm effect, that you will make something where you can see the difference between the
our condensed matter colleagues actually think that everything comes out from correlation functions. So they would claim, you know, like Zhao Gangwen and people like that, they would claim that all degrees of freedom emerge from correlations, right? So the Berry phase to them means that gauge fields, U1, maybe even non-abelian, all come out from correlations of many body as things, right, through their many body wave function and overlaps of the wave function, right? And they would also claim the fermions are essentially these fundamental things that correlate. So, you know, there are different approaches to these things depending, I guess, on your field of interest and your intuitions, but they all have merit, I would say.
Well, thank you very much. I think I've reached the end of the time allocated to me, but I really appreciated the questions and the interactions, and